Hi, we are Iztech Cengaver Rover, a student team established in 2022 at İzmir Institute of Technology in Turkey. Our team consists of 45 dedicated members from 10 different departments. We proudly participated at Autonomy Rover Challenge 2023 and 2024. Now, we are aiming to part in Autonomy Rover Challenge 2025. The team is structured into 5 specialized sub-teams: mechanical, electronics, software, science and social. Each sub-team consists of individuals who are highly competent in their respective fields. Working in harmony, these teams collaborate to design and develop a planetary surface exploration rover capable of overcoming a wide range of mission challenges. In addition, we selected our astronauts through a multidisciplinary approach and them to effectively collaborate with members from all sub-teams. Let's continue with an introduction to our sub-teams.
The design of 5 degree of freedom robotic arm is centered around one primary goal, and it is minimizing the torque requirements. To achieve this, we employed 5-bar parallelogram mechanism, effectively relocating the torque demand from first and second links to the base-mounted. This configuration provides both mechanical advantage and improved efficiency. The primary motion is driven by 2 stepper motors positioned at the base. Their rotation is transmitted through a belt and pulley system concentric nested shafts. This allows for precise motion transfer to the main links with minimal backlash and high accuracy. As a result, the robotic arm can reliably lift loads up to 8 kg. A hybrid control approach is adopted for the system, while inverse kinematics governs the links leading to the end effector. Forward kinematics is used to end effector itself. All control parameters and motion behaviors were simulated and refined using MATLAB's multibody dynamics environment. The gripper mechanism consists of 3 miniature DC motors. 2 of them manage pitch and yaw motions via triple bevel gear arrangement, while the third drives a super gear system that opens and closes the gripper. This system brings together minimal torque demand with maximum motion precision. Cengaver 2 features a dependent 4-wheel rocker suspension system with rockers interconnected by 4 rods and bearings. The rocker is designed to withstand substantial loads imposed by the robotic manipulator. A specialized unloading method has been used during the rocker's design phase to mitigate bending moments and manage inertia effectively. To produce lightweight and durable rover, we produce our material from aluminum 6061. Weight of the rover is approximately 58 kg with robotic manipulator and drilling mechanism. The largest dimension of the rover is 95 cm. This design enables the rover to navigate extreme terrain and overcome obstacles.
In our rover, we use a hub motor system as our mobility system. In this system, we use an RS775 DC motor with an RPM range of 7,500 to 15,000 RPM. We connect this motor to our predictor with GSD047.
Increases torque for our needs, such as traversing slopes and harsh terrain present in the middle. These parts are connected inside the wheel and are held in place by our ball bearings. Other parts are manufactured with 6061 aluminum except the wheel, which is manufactured with 3D printing using TPU95A. Each wheel weighs about 6.2 kg and has a diameter of 300 mm with length of 120 mm. These wheels are connected to the leg with 33 mm clearance. 2 special patterns are used on the wheel, one to help with the grip and other to work as suspension. Our rover profile is made of Sigma profiles, which has 40 to 43 cm rectangular shape, 16 cm height and 24 cm height with wheels from ground.
Our rover's electronic system is designed with modularity and performance in mind. We use a Raspberry Pi for embedded control and NVIDIA Jetson Nano for advanced processing tasks such as object recognition and autonomous decision making.
For communication, we use a 5 GHz Tenda antenna, which provides a high-speed and stable connection between the rover and the ground station. Our custom-designed PCBs and motor drivers control all the motors effectively.
Our mobility system is driven by 4 DC motors integrated directly into each wheel. We selected this configuration to ensure torque, efficiency, and robustness on rough terrains. The DC motors are controlled by using high current DC motor drivers and regulated via our embedded control system.
We built and tested the rover in our university mechatronics workshop, where we have access to 3D printers, soldering stations, and mechanical prototyping tools. For demonstration, we'll showcase how the rover performs in mobility tasks such as obstacle avoidance, rough terrain traversal, and precision maneuvering, all of which are critical to ARC mission objectives.
Our rover's manipulation system features a 3-joint robotic arm. powered by stepper motors. This gives the arm high precision and stability while performing critical tasks like sample collection and object manipulation. At the end of the arm, we have placed 3 DC motors, 2 for rotation and 1 for controlling the gripper's open-close mechanism. This configuration allows for flexible and multi-axis movements, mimicking a human hand. We choose the system because it offers both mechanical simplicity and high control accuracy.
The software team is mainly responsible for programming the autonomous and manual operation of the rover. The control is done through Rust-2 framework with C++ and Python languages for greater development experience. The main computer used is the NVIDIA Jetson Nano with Raspberry Pi Pico microcontrollers to interface with the hardware. The communication between the hardware, Jetson Nano, and the base station is done through Rust-2 messages. Every Rust package is used inside the Docker container for greater portability between the development environment and the Jetson.
Navigation 2 is used for autonomous driving, and SLAM Toolbox Kit is used for LiDAR SLAM. SLAM is an algorithm we use for mapping the unknown environment and placing ourselves into the map in real time.
For the control interface, we use Foxglove for its features like running on the browser, visualizing data, and Sportware back files, which allow rewriting the data. For debugging, we use Gazebo to simulate the rover and test how our robot might behave in real life and refine our control.
We use Raspberry Pi 2 and Raspberry Pi HQ cameras to observe environment and perform image processing. We use a wide-angle lens on our HQ camera to examine environment more easily. We calibrated these cameras and made them ready for image processing. Then we developed an algorithm to estimate the positions of the arco markers and generate arco markers.
Responsibilities of the embedded systems are controlling the DC motors, controlling the robotic manipulator, and sensor data acquisition. For odometry calculation and PID control of the motors, quadrature encoders are used. The manipulator is controlled with stepper motors using feed-forward control for sensorless operation.
As science team, we studied geology of Mars through combination of real-world data and simulated fieldwork.
We familiarized ourselves with rock classifications, sedimentary patterns, and volcanic textures. We then meshed these with open-source Martian surface datasets and elevation models. Through software like JMars and Google Mars, we simulated sample collection and terrain analysis on regions such as Mort Wallis and Solis Plano, areas with high scientific interest due to the sign of ancient water activity. By building a Mars analog database and comparing terrestrial and Martian samples, we trained Barsoom to detect and classify rock types, enhancing its autonomous exploration capabilities.
Various biochemical tests identify carbohydrates, lipids, and proteins. These 3 essential biomolecules required for the organism to survive.
Carbohydrates provide a primary energy source. Smallish tests detect the most carbohydrates. Lugol's reagent is used to identify starch, a complex carbohydrate. Lipids, vital for cell membranes and long-term energy source, are tested by using Sudan-4. Proteins and amino acids are tested by butyrate and ninhydrin reagent. The MQ series gas sensors detect gas molecules in Mars atmosphere. Hydrogen peroxide is dropped on soil samples to observe gas. The detected gas molecules provide information about biological environment. For mineral analysis, we make use of custom-designed visible spectrum spectrometer constructed in-house. This spectrometer is engineered to deliver high-resolution data, which is crucial for examining geological soil samples. It consists of a light source, a sample cuvette, a diffraction grating mirror, and detector.
The scientific sampling system can be broken down into 2 distinct modules. These are the mechanical drill system and the scientific kit. The drill mechanism works by lowering the drill assembly into the ground via rotating nut actuator powered by a DC motor. The drilling assembly is composed of an Archimedes screw with a metal rod running through it, encased in a tube with a Forstner bit at the end. The Archimedes screw is composed of small repeating 3D printed segments oriented around the metal shaft, which links the DC motor to the Forstner bit. The tube acts as a barrier against contamination between different layers of soil and a pseudo container which holds a sample until it is collected by the science kit. The drill itself fits inside a 125 by 85 mm rectangle, and its height can vary between 500 and 850 millimeters.
See you in ARC 25.